Customizing open source AI models is a lot of fun. So let's learn how to develop with the most common open source model, LLaMA. In this course, we'll take a hands-on approach to working with LLaMA, prompting, deploying, and training models. We'll use a series of Python notebooks to help you adapt LLaMA for your use cases and operationalize it for an enterprise or startup environment. I'm Dennis Linkov, Head of Machine Learning at VoiceLo, and I'll be helping you get hands-on with this amazing technology. So, let's get coding. Let's jump into a quick demo with LLaMA, since as developers, we'd rather show than tell. I'm on the Hugging Face chat website. Hugging Face is an open source ML ecosystem, and on their chat website, they allow you to try a number of models for free. I'm going to go ahead and switch my model to LLaMA 2 70 billion parameters chat edition. I'm going to do this by clicking on the gear icon right here and clicking on Meta LLaMA LLaMA 2 70B Chat HF. I'm going to click the Activate button. I'm going to exit, and now we can type in a prompt. I'm going to type in the prompt, "Why is the sky blue?" and hit enter. And there we go, we got a response. Now what is LLaMA? LLaMA is an open source model family released by Meta in 2023, and it performs well on many tasks including Q&A, classification, and logical tasks. There are actually many websites that let you play around with LLaMA 2, but I like the interface of Hugging Face. Now in the next video, we'll run a version of LLaMA 2 in a Python notebook ourselves. Let's run LLaMA in our own cloud environment. You can find the code for this exercise under branch 0102 on GitHub. For this course, I'm going to be using Google Colab, which is a free Jupyter Notebook environment. Let's go ahead and launch it by hitting Open Colab. So in Colab, I can start off with either uploading a file or using a GitHub integration. On the GitHub integration side, I have my personal GitHub here. We can go ahead and enter the LinkedIn Learning account. At the GitHub integration, you'll be able to clone either your own repository or any public repository. Now let's go ahead and select our LLaMA course and select our branch, which is 0102. Now in this case, I've already downloaded the code, so let's go ahead and upload it. It's 0102 as a Jupyter Notebook. Let's hit open, and here we go. So at the top here, I have some instructions for running this model. While LLaMA is an open source model, it does have some conditions associated to it. Let's go ahead and read them. So to gain access to LLaMA, you need to request it by having your first name, last name, and some personal information filled out. You can then fill out which models you want access to, and read this agreement to make sure you understand what's going on. Now the general agreement states they won't do anything harmful with the models, but I'd go through and give this a thorough read. After accepting the conditions, we can go ahead and gain access to the model in Hugging Face. I'm here under the Meta LLaMA organization with LLaMA 2 7B Chat Hugging Face. Now you can see here, it's stated that this is a gated model, but I've been granted access. So on your screen, you may see something like this, Access LLaMA 2 on Hugging Face. So in this case, you will enable LLaMA 2 on Hugging Face by gaining access through Meta. So that's the form that we saw earlier. Now, when you gain access, you should receive an email looking something like this. This is to let you know your request to access model Meta LLaMA LLaMA 2 7B on huggingface.co has been accepted. All right, great. Now let's head back to our repository. So we've read the license, we requested access to Hugging Face LLaMA 2. Now let's go ahead and create our Hugging Face token. Now to do so, we need to go ahead and go back to Hugging Face and create an account. In this case, it was pretty easy just using my Gmail. Afterwards, we can go to Settings, go to Access Tokens, and grab our tokens here. I've created one called LinkedIn. I'm going to copy my token. Let's head back to our repository. In this Colab notebook, let's scroll down and add our token. We can see right here on this access token portion. I'm going to go ahead and paste it. Okay, let's scroll to the top. Now, our next step is to install these libraries. So we're going to install the transformers library, bits and bytes, and accelerate. Let's go ahead and do that. I'm going to click into this box here and hit Shift-Enter. Now what will happen here is we'll initialize our GPU access, in this case to a T4 GPU, and we're going to install all our repository dependencies. All right, let's go to the next portion. Now in this portion, we're going to import our Python dependencies, transformers and PyTorch. Now here we have our model name, which is LlaMA 2 7B ChatHF, our access token, and our quantization configuration. We don't need to worry too much about that. We'll discuss it in another video. Now in these final two lines, we're going to download the model and the tokenizer. This will take a little bit of time. Now we can see here, the model has been downloaded and we have initialized the tokenizer. If we keep scrolling down, we can see we can run our prompt. So I'm going to run this prompt. What is 2 plus 2? Answer concisely. Let's hit Shift-Enter. Now looking at the previous output, you could see that LlaMA 2 7 billion parameters can be a little bit verbose. So let's hope that this time the answer is actually concise. All right, here we go. We got a response. In this case, the response was quite verbose. And that's because LlaMA 2 7 billion parameters is the weakest out of the LlaMA family. Now the reason that we had to use a weaker model is because we had to fit it on just one small GPU. We're running a T4 that has 18 gigabytes of video memory. Now that might seem like a lot, but for large language models, that's a very small amount. If we scroll up, you can also see that we're running the model in a 4-bit quantized mode, meaning that we're only using 4 bits rather than the standard 32 bits for holding the model parameters. This will also affect the performance. So there we go. That's how we can run our model in a Colab environment. In the next video, we're going to cover how we can run a LlaMA model in an enterprise environment. In this video, we're going to learn how to run LlaMA in an enterprise environment. Most enterprises have special rules for running Gen AI, and this includes LlaMA. The easiest way to do so is to run a managed version of LlaMA and call it through an API. Let's go through some examples. The first example is running LlaMA on Azure's AI Studio. I'm here on the ai.azure.com, and I'm under LlaMA 2 70 billion chat. You can see here I can deploy the model under the deploy option, running it as a pay-as-you-go, which is running it continuously, or as a real-time endpoint. Now you can do the same thing on a number of different vendors. I can do the same thing on Amazon Bedrock, or on Google's Vertex AI Model Garden. Many companies also use Databricks to host and run their large language models, as well as the Hugging Face Enterprise option. Now your company may already have LlaMA or other Gen AI models running on their on-prem or cloud environments. In that case, all you have to do is call an API. But if you want to play around with LlaMA on your local environment, you can also do that. You can download it, just like we did in the Google Colab, but on your local machine. Keep in mind that these models are quite large, so you need to have the corresponding hardware to run them. So that wraps up this chapter. We know that we can run LlaMA 2 in enterprise-grade environments and access them via an API. In the next chapter, we're going to dive deeper on how LlaMA actually works and understand its underlying components. So we've used LlaMA, but how does it work? Today we're going to cover the LlaMA 2 architecture and its different components. LlaMA is a large language model, specifically a decoder-styled one, meaning that it accepts inputs, passes it through a program called a tokenizer, and then predicts the next token. Now what exactly is a tokenizer? The tokenizer helps transform input into numbers that the large language model can understand. In this example, we have what is 2 plus 2, answer concisely. These get mapped to some tokens, which aren't exactly words, they're not exactly characters, they're something in between. We'll talk about this more in a future video. Now once the input is mapped to tokens, we'll be able to predict the next token as part of the training output. We go ahead and input something into the model, for example, a robot must, we get the output, and then if it's not correct, we correct it and propagate that error through our model. Now, when training models or using models, you might have heard of something like model size. 7 billion, 70 billion, what do these things mean? These numbers stand for the number of parameters as part of the model. You can think of a parameter as a tiny little transformation that happens on the model input. When you have more parameters, the more complex your model is. Now, if we go to simpler neural network, which makes up these large language models, you take an input, you process it through some hidden parameters, and then you get the output. Now, for large language models, the architecture is usually a bit more complex. In the case of LLaMA, we have an input layer, a normalization step, our attention layer, another normalization step, and a multi-layer perceptron, which is a fully connected neural network. Now, for the scope of this course, you don't need to understand all these components. Just understand that there's a lot of computation happening behind the scenes. From the LLaMA 1 paper, Meta does provide us some additional context, particularly the hidden dimensions of the models, the number of attention heads, and the number of layers. If you're interested in learning more about the architecture, I recommend you read the LLaMA 1 paper. Now, the final component of the architecture I want to touch upon is the context window. The context window is how much tokens a model can input and output based on the current architecture. As you can see here, there's a difference between LLaMA 1 and 2, which we'll discuss in a future video. In the next video, we're going to dive deeper into the LLaMA tokenizer, so we understand how it maps input from a user into input into the model. So we've probably heard about LLMs using tokens, but what exactly are they? Typically, when we explain tokens, we say that they're kind of similar to words, but let's dive deeper. A token is a way to represent components of an input into a model. This could be characters, words, sentences, or numbers. In some multimodal models, it can also be images, sounds, and videos. In the past, prior tokenizers were hand-coded, based on language rules typically around punctuation or words. But the idea of tokenization being different was first introduced in 1992. Since then, there have been many tokenizers that have been trained, with billions of words utilized to train the best tokenizer. Some of these tokenizers have been character-based, others have been prefix or suffix-based, and others have been word-based. But each tokenizer is a little bit different. In the case of LLaMA, LLaMA uses the sentence-piece tokenizer, which was developed by Google. Now, how do you get the representation in a tokenizer? You do so by training a tokenizer based on some data. The data should be pretty representative of your actual model training data to make sure that the tokenizer can understand it well. Now, there are three main goals of a tokenizer. The first goal is compression, making sure that your data can be represented in a small amount of tokens. The second one is representation, making sure that you can handle edge cases as well as common patterns in your tokenizer. And the third one is performance. The first two goals don't matter unless you can get a model that performs well. Now, each tokenizer is a little bit different. In this case, we take sentence-piece, which is our LLaMA tokenizer, and compare it against TickToken, which is the current OpenAI tokenizer for models like ChatGPT. Now, when you have uncommon tokens, you usually get worse performance. This is because the models cannot learn how to associate them together. Now, in the case that the tokenizer's training data is different than the input data, you might get pretty poor compression. I wrote a blog post about this, comparing how the GPT-2 tokenizer compares to multilingual tokenizers. The results indicated that to represent the same sequence in many languages, GPT-2 required a lot more tokens in less represented languages than traditional multilingual models. This means you'd use a lot more tokens for multilingual input and output. Now, going to the key question, why is a good tokenizer important? A tokenizer needs to represent learnable patterns for the large language model. Going into an example with code. If we have a simple Python program, we expect our tokenizer to be able to understand it well. If we look on the right-hand side on the tokenization, we can see that equals and double equals have their own tokens because they're used in different ways. We can see that 4 spaces also make up one token because they're quite common in Python as a representation. We also see that opening quotes and closing quotes are quite different. In this case, the tokenizer worked well. It can represent our code in a compressed yet representative way, and the models used downstream have pretty good performance. In the next video, we're going to talk about LLaMA's context window, how many tokens you can fit into a single input and output. If you've worked with large language models before, you've likely gotten the context window exceeded error. But what is it and why does it exist? In this video, we'll dive deeper into context windows and what LLaMA's context windows can accomplish. Now, context windows are the combination of input and output tokens. And the reason that they're limited is because we need to make sure that the relationships can be successfully mapped. As an analogy, think about verbal communication. If I was to whisper to you, you'd need to be in a close hearing range, maybe a meter. Now, if I was yelling outside, you might be able to hear me from 30 meters away. Anything more than that, and we wouldn't get good communication results. In this analogy, this is why large language models are limited. The technology does not allow us to comfortably go beyond this context window. Now, if we go through historically, in 2018, when BERT was released, the context window was 512 tokens. Next was GPT-2 in 2019 with 1,024. Then GPT-3 in 2020 went 2,048. And nowadays, we're seeing models with tens of thousands, hundreds of thousands, or even millions of tokens. So why are these context windows changing? Now, the main reason we were limited before is that attention, a key part of our model architecture, is quadratic, meaning that for every additional token, we have a quadratic relationship with the amount of memory we use. Eventually, it becomes too computationally intensive to add larger context windows. We'd need too much memory. Now, in recent years, in 2023 and 2024, we've developed a number of techniques to improve our ability to handle quadratic attention. Some of these techniques include rope, linear interpolation, flash attention 2, and grouped query attention. Now, for the scope of this course, you don't need to know too much about these. Just know that we're developing techniques that can extend our context window beyond our traditional number. Now, when LLaMA 2 was released in summer of 2023, its context window was 4,096, being able to fit around 20 pages of text within it. Now, since then, there have been a number of LLaMA variants trained, with context windows of 32,000 and beyond. Now, context windows will likely continue to evolve as our technology and large language models continues to step forward. In the next video, we're going to talk about some of these evolutions, comparing LLaMA 1 with LLaMA 2. LLaMA 1 was released in February 2023 and made immense progress in the world of large language models. A few months later, LLaMA 2 was released and became the standard for open source models. So what changed? In this video, we're going to cover the key differences between LLaMA 1 and 2. The main differences are the licensing of the models, the training data composition, and the fine-tuning techniques used. Let's talk about the licensing. Now, when LLaMA 1 came out, it was distributed under a non-commercial research license. Meta's goal was to help maintain integrity and prevent misuse. Now, 6 months later, this narrative changed completely. LLaMA 2 was released under both a research and commercial license. The commercial license is fairly light, something that we read through earlier. So the shift between a restrictive license and an open license for the model weights were quite different. So what were the impacts of these different licenses? Well, after LLaMA 1 came out, the weights were leaked and shared throughout the internet. Now, the research community still continued to develop a number of different variations of LLaMA, naming them after llama's biological cousins. Now, when LLaMA 2 came out, we got many more variations, and because it was open for enterprises, we saw many platforms adopt them. As we covered earlier, platforms like Azure, GCP, AWS, Databricks, and many more were now deploying LLaMA 2. Now, just based on this licensing change, we saw much greater adoption of the model. Now, the third key difference was LLaMA's training data. In LLaMA 1, the training data was well described in the paper, using around 1 to 1.4 trillion tokens for each training run. In LLaMA 2, there's a new training data mix, data available on the public internet, but the exact mixture was not well described. LLaMA 2 also used 2 trillion tokens, which is largely attributed to why the performance was better. The current research methodology suggests that adding more tokens to training models usually results in better performance. So this wraps up our theoretical chapter on LLaMA. In the next chapter, we're going to get hands-on on training LLaMA. In this chapter, we're going to learn how to fine-tune a LLaMA model to improve its performance on a specific task. Now in this video, we're going to start off with a basic fine-tuning. We're going to do this for a sentiment classification model. I'm here in O301B, and let's connect to our A100 GPU. Now for training LLaMA, even the 7 billion parameter one, we need to use an A100 GPU. If you don't have one as part of your Colab subscription, that's okay. You can just follow along. Now here I've outlined the 6 steps we need to fine-tune our LLaMA model. First, we're going to install dependencies. Then we're going to load our model. Then we're going to run our test prompt on the initial model itself. Afterwards, we're going to create our fine-tuning dataset, run training, and test the prompt again. So let's get started. I'm going to go ahead and install our dependencies. The 2 new dependencies here are the datasets one, which contains our sentiment classification dataset, and TRL, which we'll use for fine-tuning the model. Now let's scroll down. We're going to download our standard LLaMA model. We're going to load it in a 16-bit version since quantized models don't perform as well in training. So let's go ahead and hit Shift-Enter. Something that might pop up is if you're running this notebook for the first time, is you might need to grant access to your Hugging Face token. That's okay, let's hit Grant Access. Now we're going to download the model. Alright, here we go, we've loaded our model. Next, let's go ahead and load our tokenizer. One extra thing that we'll need to do for training is set our pad token. A pad token is what we'll use to differentiate one training example from another. Now scroll down. Next, let's go ahead and run our prompt. We're going to do this for the original model. Now we've generated the output. We need to add one more step, which is decoding it and printing it out. Let's go ahead and add a code block right above by clicking the code button. And let's type out decoded equals tokenizer.decode. We'll pass in the output with the first value, so index 0, and we're going to skip special tokens, set that to true, and finally hit enter, and we're going to print decoded out. We'll hit Shift-Enter. There we go, we got our response. Now, unfortunately, the base version of LLaMA did not complete this task very well. We did not classify the sentiment as a number. It also kept going with additional output. Alright, let's go ahead and fine-tune our model. We're going to scroll down, and we're going to load our dataset in. I'm using the Hugging Face IMDb Reviews dataset, and I'm going to grab the first 2% of the training data and the last 2%. That's because the dataset is sorted by positive and negative reviews, so I want a balance of each. I'm going to do the same thing with our test dataset. Next, I'm going to create a prompt that has instructions in it. So I have instructions for classifying the sentiment into a number, and I'm going to pass in the input, which is the review, and the response, which is a number, which is 0 or 1. So let's go ahead and run this process. All right, here we go. We've downloaded the dataset and we split it up. Let's give you a quick preview of what it looks like. The next cell has the information about it. So here we go. We have our dataset, 1,000 items each. We have our prompt, and we have our response, as well as the positive and negative values, which are represented as 1 for positive and 0 for negative. Now let's keep scrolling. Here we're going to set up our trainer to train LLaMA. We're going to be using the TRL Supervised Fine-Tuning Trainer, or SFT trainer. We're going to configure training arguments, most of which are beyond the scope of this video. But we're going to pass them into the trainer, along with our data, tokenizer, and model. Now let's go ahead and hit Shift-Enter. All right, great. Our trainer is ready to go. Let's go ahead and hit Shift-Enter to train the model. Oh no, it didn't work. We're out of memory. So unfortunately, using standard methods won't work to train our 7 billion parameter LLaMA. In our next video, we're going to cover a technique so we can train this model by freezing some of the layers. So it turns out fine-tuning LLaMA isn't as easy as it seems. And that's okay. That's the fun of working with AI. In this video, we're going to cover the techniques we need in order to enable our fine-tuning. Let's go into the second cell. Let's talk a little bit about how much memory we need for training our model. So there are 3 key things that affect our model memory for training. The first one is loading the model parameters onto the GPU, which takes up 4 bytes per model parameter. The second one is the optimizer, which uses 8 bytes per model parameters. And the third one is storing the gradients, which requires 4 bytes per model parameter. Now if we add all these items up, we get 16 bytes per model parameter. Now multiplying that by 7 billion parameters, we require 112 gigabytes of RAM. That's a lot. Now we can reduce this by doing 3 techniques. The first one is freezing LLaMA layers to reduce our trainable parameters. The second one is quantizing our model or reducing our precision. And the third one is to use a smaller optimizer. And our goal is to get down to less than 40 gigabytes of GPU RAM. Now if you're interested in learning more about these optimizations, I've included a link to Hugging Face. In this article, they go into more depth about what it takes to train a large language model. Let's head back to our notebook. So we're going to get started by installing our dependencies. As you can see here, we've added bits and bytes back into our dependencies. The reason for that is we're going to use some quantized parameters. So let's scroll down. Next, we're going to download our LLaMA model. We're going to load this model in a 16-bit option, so we can reduce the precision that we have and the amount of space that the model takes up in our RAM. So we've downloaded our model. Now one thing to note is that I'm still using an A100 GPU. We'll be needing the 440 gigabytes for this video. If you don't have an A100, you can just follow along. My code, once again, is under 0302B. Let's keep going and download our tokenizer and dataset and print our dataset contents. I'm going through all of this with my Shift-Enter. And let's scroll down. All right, now I have a code snippet here to add the model freezing code. So let's go ahead and type out the number of layers we want to freeze. We'll set nFreeze equal to 24. So LLaMA has 32 different layers, so we'll freeze 24 out of 32 of them, leaving 8 to train. So let's go ahead and freeze all the layers. We're going to type out for param in model.parameters. So loop through all the parameters of the model. Param.requires grad equals false. All right, so we're going to freeze all the model parameters. The gradient is similar to freezing the parameters. Next, we're going to unfreeze the model head parameters. So we'll type out for param in model.lm head.parameters. So these are the output parameters. We're going to do param.requires grad equals true. And now we're going to unfreeze the layers that we want. So layer 25 and onwards. For param in model.model. This is funky syntax, but it's okay. We'll type out layers, pick our layers, so nFreeze to the end. I'll call parameters on it. And we're going to set the param.requires underscore grad equal to true. All right, that looks good. Now finally, we're also going to freeze the embedding tokens. So these are the token values at the front of the model that we transform via the tokenizer. So let's type out model.model.embed tokens.weight.requires grad underscore bracket false. All right, there we go. A little bit of a mouthful, but we're ready to unfreeze the model. So let's go ahead and run that. There we go, we get the output. And next up, let's go ahead and look at our trainer. Now we've done the first two steps. We've loaded the model at a 16-bit precision. We've frozen some layers. Now it's time to change the optimizer. We're going to use the Atom W 8-bit. So we're only going to use 2 bytes of information per model parameter. Now to do that, we'll need to import the bits and bytes config, since it's part of that package. Now everything else should be the same as in the last video. Let's go ahead and run our training. I'm going to hit Shift-Enter to generate our trainer. All right, great. And Shift-Enter to run our trainer. Now at the top right, we can take a look and see how our GPU usage is going. I'm going to click on A100, and now I can see my GPU RAM. It's increased up to 24 gigabytes, but it's not at the 40 max. That's pretty good. And now we're going to run evaluation. So as part of this exercise, we should see 2 different losses. The training loss represents how well we fit the data to our training data. The validation loss represents our loss on an unseen data set, so to represent how well the data generalizes on a broader data set. Now let's wait for this training to finish. As we can see here, our GPU usage is spiking, but to 37 gigabytes rather than the over 100 that we expected before. That's great. So let's scroll down, and we'll see our final evaluation score. All right, here we go. We finished our training. Our training loss went down quite a bit, but on our second epoch, our validation loss only went down a little bit. But that's okay. So let's go ahead and run our fine-tuned model onto our prompt. I'm going to hit Shift-Enter to run our prompt. Now you can notice here, I'm using this Torch CUDA AMP autocast. This is because we're converting between different floating types, so we use this method to let the GPU handle it. Let's scroll down, and we're going to run our decoded. All right, there we go. This response is better. We got our number, which is 1, meaning a positive sentiment, after our input of "it was a great movie." Now, this fine-tuned model isn't perfect. We only used 1,000 examples, so we didn't override LLaMA's tendency to ramble a little bit. Now, in the next video, we're going to learn another technique of fine-tuning with fewer resources. It's called LoRa. In the past video, we learned how to fine-tune a LlaMA model by freezing some layers. In this video, we're going to learn a technique called LoRa. LoRa has been quite popular recently, so let's go through the original paper and see how it works. Now, the LoRa paper was introduced in 2021, focused on the ability to train larger models like GPT-3. The benefits were that you can fine-tune the model by adding fewer new trainable parameters, having higher training throughput, and having no additional inference latency. Now, quick architecture on how LoRa works. LoRa works by connecting to the linear layers of a large language model. These are fully connected neural networks. Then, by projecting the information into our lower rank space, it's able to learn this information and combine the output at the end. Now, this paper is more technical than that, but that's the key idea. Now, if we keep scrolling, the authors indicated some additional advantages. We could keep the model pre-trained and only build and share additional LoRa modules. Now, this is pretty awesome. It's actually what we're going to do by the end of the video. We're going to train our own sentiment LoRa and share it on the Hugging Face Hub. And the second benefit is LoRa allows us to train more efficiently and on smaller hardware. So you'll actually be able to fine-tune your LlaMA model on a T4. And the third benefit is that running our inference code will take just as little time as it did before, which is pretty awesome. Now, the fourth benefit here, it's beyond the scope of this course. So let's head over to our notebook under 0303. So I'm connected to an A100 just to speed this process up. Now we're going to install our dependencies. One dependency that you'll notice that's different is the PEFT, which is the Perimeter Efficient Fine-Tuning Library from Hugging Face. So let's go ahead and install our dependencies. In the starting notebook, there's already some output. That's because I ran it before. Now the outputs might change time to time, but that's okay. The core idea is still here. Let's scroll down. Now to get us started, we're going to load our model in a 4-bit quantized configuration. LlaMA allows us to do that. So let's go ahead and run Shift-Enter. And here we go. We have our LLaMA model loaded. Let's go ahead and load our tokenizer. We'll hit Shift-Enter on the next cell and scroll down. And after that, load our dataset. We'll also print out our dataset once this is done. There we go. Now let's keep scrolling. Now this is where the fun starts. We're going to import this LoRa config from our PEFT library. So in this one, we're configuring a bunch of LoRa parameters. Now the one I want you to focus on is this target modules. These are all the linear layers we're going to be connecting to as part of the LoRa training. So once we configure that, we can go into our training arguments, where we pass in a batch size of 6 and eval size of 48. For our learning rate, this is the main change. We've increased the learning rate because we're now training our LoRa adapter rather than our base model. And we're still going to use our AtomW 8-bit optimizer for reduced memory consumption. Now finally, we're going to pass in our PFT config into our trainer. So let's go ahead and run this, hit Shift-Enter. And once that's done, we're going to train the model and hit Shift-Enter. Let's open up our GPU usage to see how we're doing. We're going to go to the top right and click on our A100. You can see that we're under our 40 gigabytes of GPU RAM, which is great. So we've trained for one epoch, and now we're doing our evaluation. All right, here we go. It looks like our training loss and validation loss are doing pretty well. All right, here we go. We've trained our LoRa adapter, and the loss looks pretty good. So what we can do now is we can save this model locally. We're going to run trainer.savemodel. On the left-hand side, we're going to click on this file folder and see LoRa is saved here, with all the different files that we need. And now to run this specific LoRa model, we're going to load it from disk. I'm going to hit Shift-Enter. Once the model is loaded, we're going to go ahead and run our original prompt through it and decode it. All right, there we go, that's great. And the response was a 1, which is correct. That's a positive sentiment. But unfortunately, LLaMA 7 billion parameters still generated additional output. Not great, but we can certainly use a larger training set for the future. Now, in order to push our model up to the Hugging Face hub, all I have to do is run this push to hub command. And once it's done, it'll look something like this. I've shared my model on Hugging Face. I can add some additional model descriptions, but I'll do that later. Now to do so, we need a write token. So let's go to our settings by clicking on our profile and settings, grab our access token, and as you can see here, I've created an upload token. Now I'm going to paste that upload token into my secrets. So now I have an upload token rather than a read token. In the future, if I want to upload another model, I can go ahead and follow the Hugging Face documentation. It's pretty good. Now going back to our notebook. As you can see here, we learned another technique for fine-tuning our models. We were able to train our models with fewer than 40 gigabytes of memory and successfully run it on a prompt. In the next video, we're going to talk about other fine-tuning techniques, specifically human preference and direct preference optimization. We referenced these techniques in the previous LLaMA architecture video, so we'll get to put them into practice. One of the key insights from the LLaMA 2 paper was the use of reinforcement learning with human feedback, or RLHF. This method leverages the ability to have humans rate different prompts and create a model that trains on top of LLaMA to fine-tune it. Now in this video, we're going to cover two preference techniques, RLHF and DPO. DPO stands for Direct Preference Optimization. So let's learn a little bit more about RLHF. RLHF works by creating a reward system, where we train the data and create a reward function. This could be helpfulness, this could be harmlessness, as we've seen in the LLaMA 2 paper. Now reinforcement learning is quite complex. So for the purpose of this video, we're going to use another technique called DPO, or Direct Preference Optimization. Let's head over to our collab. I'm in 03_04, and I'm going to be using an A100 GPU. Now for this video, we're going to do something very similar to our LoRa training. We're going to train a LoRa model by using direct preference optimization. Let's go ahead and install our dependencies and download our model. I'm going to hit Shift-Enter and scroll down to our model. For our model, we're going to be using the 16-bit precision, just because of the way that the DPO library by Hugging Face interacts with it. So let's go ahead and download it by pressing Shift-Enter. Next, scrolling down, we'll activate our tokenizer and go over to the datasets. Now for our dataset, it's very similar to our previous video. We're using IMDb and sampling from the training and test side of things. Now for this video, we have changed our prompt. We have our formatting prompts function, and what we're going to do is create two different variations, a chosen variation and a rejected one. In the chosen variation, we're just going to put our classification. In this case, if the model sentiment is positive, it's going to be a 1, and if it's negative, it's going to be a 0. Now in the rejected one, we're going to have two different types. The first one is we're going to add extra output. For example, this ### instructions. We've seen that before, we want to fix it. We're also going to add the wrong answer, inverting it if it's a 1 to a 0, and if it's a 0 to a 1. And then we're going to construct our dataset. Let's hit Shift-Enter, and we'll also print out the results. So you can see here, we have our dataset, we have our prompt structure, and we have our two different responses. Chosen one is a 0, which is correct. The rejected one is a 0 and instructions. All right, that looks good. Let's keep scrolling. Now we're still going to be using TRL and LoRa config, but instead we're going to import the DPO trainer. And the DPO trainer works in a very similar fashion. We need to configure our training arguments. In this case, I've changed my batch size to 2 because we're not using a quantized model. And we configure our LoRa configurations. Now scrolling down to our DPO trainer, things are very similar. The main difference here is that we set a beta parameter, which is a hyperparameter that we use for DPO. Everything else is fairly similar to our previous LoRa trainer. The other difference is the max length and the max prompt length, but these aren't too important. So let's go ahead and hit Shift-Enter. All right, that's great. Now we're going to go ahead and train our trainer. After training our dataset, we'll see that our training loss and validation loss are a little bit different. You can see here we have the rewards chosen versus the rewards rejected. And we can see the accuracy of each of these rewards. We have a bunch of metrics to see how our model responded to each of these preferences, based on the chosen and rejected categories. And there we go. We've trained our model. Our training loss and validation loss are successfully lower. So let's go ahead and save our model locally with the next command. And now let's run our prompt through our newly trained model. Wow, this is great. 1.0 is a much better response than anything afterwards. It's still not a 1 or a 0, but close enough. Now the final item is to push this model to the Hugging Face hub. So I'm here on huggingface.com/new, and I'm going to create a new model. I'm going to call it sentiment-LoRa-DPO and create model. So let's copy that name, go back to our notebook, paste it in. So let's go ahead and push the perimeter efficient model to the model hub. Now we haven't defined an explicit variable, so let's replace it with trainer.model.push to hub. Let's go ahead and press Shift-Enter. There you go. We can see we're pushing our 100 million parameter model. And it's a success. Let's go to our model page on Hugging Face and refresh. And there we go. We've successfully pushed our sentiment LoRa DPO tuned to our Hugging Face website. In this video, we learned about how to use a human preference dataset to fine-tune a model. In the next video, we're going to learn how to fine-tune larger LLaMA models. Now in this video, we're going to cover how to fine-tune larger LLaMA models. Right now, we're here on the LLaMA GitHub page. Now, one of the limitations of LLaMA is that you can only fine-tune a 65 billion parameter model, which is original LLaMA, on a 48 gigabyte GPU. Now the challenge here is our A100 only goes up to 40 gigabytes. So unfortunately, we need to find another method. We can always use multiple GPUs, but in this case, we don't have it available on Colab. So for this video, we're going to go through a more theoretical approach on how to fine-tune a larger model. LoRa and freezing some layers are great ways to fine-tune larger LLaMA models. The alternative is we can use a third-party vendor. For example, Together.ai lets you fine-tune a 70 billion parameter model. As you can see here, they have a pricing calculator on their website to estimate the cost. So for a 70 billion parameter model and 100 million tokens, it would cost around $321. Now, our previous data set was around 100,000 tokens, so that would be around $5. Not too bad. Now, beyond using a third-party vendor that has more access to GPUs, thankfully, training larger models is an active area of research. Just yesterday, March 6, 2024, a new paper came out about using a new optimizer called Galore. As we can see here on this diagram, using 8-bit Galore allows us to fine-tune a model on just 24 gigabytes of memory. That's pretty awesome. Now, these advancements will continue to develop, and hopefully we'll see them in our practical libraries that we use, such as Hugging Face, going forward. The other news from yesterday was that Answer.ai has developed a new technique to train 70 billion parameter language models on just 2 GPUs. Based on a distributed computing platform called FSDP from Facebook and LoRa, which we've used before, researchers from Answer.ai, Tim Detmers, who built LoRa, and the Hugging Face team are releasing this new technique. So going back to our original question, how do we fine-tune 70 billion parameter models? Currently, it's quite the challenge, but hopefully, in the near future, it'll be easy to do so just in a collab. So this wraps up this chapter. In the next chapter, we're going to be talking about serving LLaMA, starting off with the requirements required to serve one model. So we've done a quick demo before of serving LLaMA, but what resources do you really need? In this video, we're going to go through some LLaMA serving requirements. These include fitting the models into the RAM, calculating throughput, real-world throughput examples, and a few optimizations. So in order to load a model, we need to fit it into our hardware. To do this, we need the correct amount of RAM or video RAM. Now, to load a model of a specific size, we need to multiply the precision of the weights, which are typically stored as 32-bit or 4-byte, by the model size. So if our LLaMA model is stored in a 32-bit format, and it has 7 billion parameters, we would require 28 gigabytes of RAM. Now, if it's 13 billion parameters, it'd be 52. And if it's 70, it'd be 280. You might be wondering, in previous videos, we loaded in a 7 billion parameter model into 16 gigabytes of RAM. How did that work? Well, we used a technique called quantization. Model weights can be stored in a lower precision, from 32-bit all the way down to 4 bits in the current state of the art. And with decreasing precision, we need less RAM. So a 16-bit LLaMA that's 7 billion parameters only needs 14 gigabytes of RAM. So memory is our main limitation to actually loading the model. Let's go through and calculate the throughput to get our next token. Now, our model speed is bound by 2 factors, the computation speed and the memory bandwidth. Let's look at a standard GPU like a T4. A GPU can generate up to 65 teraflops, which is 65 trillion floating point operations per second. That's a lot. If we take our 16-bit LLaMA, which is 14 gigabytes in size, at full power, it would still take 0.21 milliseconds per token to move 14 billion parameters around. That's how big these large language models are. Now, from a bandwidth perspective, the T4 has 320 gigabytes per second worth of memory bandwidth, so that would take around 44 milliseconds per token. Now, in practice, we never achieve these real rates. These are just our theoretical maxes. Now, depending on the model we're running and on which hardware, we can either be having a compute or memory-bound system. If we have a high-throughput system, we're likely compute-bound. Now, in the more complex cases, we could even be network-bound, assuming that we have lots of GPUs connected together. Now looking at some real-world benchmarks. For LLaMA 7 billion and 13 billion parameters, you might get around 20 milliseconds per token in latency. Now with ML models, there's usually a throughput versus latency trade-off. We can maximize our throughput by sending more data in through higher batches, but this means that our latency per token is likely going to be higher. Now we can increase throughput with some tricks, similar to computer operating systems. In 2023, there's a new technique developed called paged attention. What this means is that the attention blocks that we learned about earlier are cached in a smart way similar to computer systems. Now, with the development of paged attention, throughput of many LLMs increased by 2x, even on standard graphics cards. That's pretty amazing. Now, apart from paged attention, there's a number of other tricks. We talked about quantized models. You can also compile or fuse the model operations to make sure that in a single pass, your GPU is used most effectively. There's also a technique called speculative decoding, where you use a smaller model to generate the initial tokens and a larger model to finalize them. There's also been changes to attention, with Flash Attention 1 and 2 coming out. You can also optimize your batching ratio, balancing throughput and latency. And lastly, there's been a lot of interesting work about offloading your GPU workloads to the CPU and RAM. Now, there are many more tricks, and these will continue to develop, so don't worry if they seem overwhelming. The goal of this video is to provide you a sneak peek on the mysteries and magic of large language models serving. In the next video, we're going to talk a little bit more about quantizing LLaMA and why we can serve the model at its current precision. In the previous video, we talked a little bit about fitting LLaMA onto your hardware. In this video, we're going to dive deeper into quantizing LLaMA. So to start off, why is quantization important? There are 4 main reasons. The first one is it allows you to run more powerful models by reducing the memory footprint. The second one is it allows you to train more powerful models. The third one is that it reduces energy consumption. And the fourth one is that it advances computer science. Now recapping quantization, from the previous video we saw this chart. Depending on the precision that we store our model, we require a different amount of memory. Original LLaMA would require 28 gigabytes of memory, while 4-bit quantized LLaMA only requires 3.5. Now quantization is fairly new. We only achieved reliable 8-bit quantization for large language models in 2022. So with that said, let's review some of the important blog posts and papers about quantizing large language models. So to start off, let's take a look at this blog post about 8-bit matrix multiplication. Now, this blog post originates from a paper written in 2022. This paper talks about the unique challenges of trying to quantize larger models. If we scroll down to page 2 and zoom in, we can see here that once a large language model gets big enough, the performance drops significantly. Now, the reason with this has to do with matrix multiplication outliers, meaning that some of the loss of precision propagates through the different layers and leads to a loss in value. Now, this paper is very interesting, but generally beyond the scope of this course. The important thing here is that this technique for quantizing for 8 bits is quite modern. Now, heading back to the Hugging Face blog, we can see another blog post about 4-bit quantization. Now, this blog post is written by the same authors and builds on the existing paper. Now, if we go into the paper, we see that this one is focused on model training, the ability to fine-tune models with even lower precision. Now, if we scroll down to page 8, we can see the performance of LLaMA with different levels of quantization. We can see here that the 4-bit LLaMA performs pretty similarly to the 16-bit LLaMA, which is a pretty amazing achievement. Now, what you might have noticed from these blog posts and papers is that these techniques are utilized in bits and bytes. This library is the one we used in one of our first videos of serving LLaMA, and is now a key component of almost all large language model serving architectures. Now, something that you might notice from this blog post is that 4-bit quantization works with model training. Why is that important? Let's head over to another blog post talking about model training. This blog post by Hugging Face discusses the optimizations that you can do to train on one GPU. Now, quantization isn't just important to model weights, It's also important to the optimizer state for training. These optimizers help our model know when it's training how to correct its previous errors. So a standard optimizer, like AtomW, uses 8 bytes per the number of parameters. But you can quantize AtomW to 2 bytes, significantly decreasing the amount of memory that you need for training LLaMA. So what is the impact of quantizing models? If we go to the Hugging Face Hub, we can see that there are over 1,600 models that have 4-bit in their name. These models include extremely popular versions of open source models, like LlaMA and Mistral. So quantization isn't just interesting from a theoretical perspective, it's enabling us to serve larger and larger models at scale. In the next video, we're going to dive deeper into running large language models. We're going to set up our first LLM server. If you remember at the start of this course, we used the Hugging Face chat to interface with LLaMA. Now, how is this LLaMA running? It's a 70 billion parameter version, so it requires quite a bit of hardware. Now, Hugging Face open sources a server that runs this interface. It's called TGI, or Text Generation Inference. Now, this is a library and web server that allows you to serve many large language models. Here's a quick architecture diagram from the Hugging Face documentation. TGI is mainly written in Rust and connects over gRPC to different models. These are sharded over various GPUs and can support a number of different vendors. If we scroll down, we get a list of nice built-in features. It's easy to use, production ready with tracing and monitoring. We have parallelism, token streaming, and many more. So rather than just running a fast API server with your favorite model, the recommendation is to use one of these frameworks. Let's look into the GitHub code. So you can see here, I'm in the repository, and if we scroll down, we have some documentation on how to start the TGI server. Now for the core information, I've put it in our Jupyter notebook under 0403. So in here I have a couple components. The first one is launching the server. So the recommended method to launch TGI is through Docker. The reasons for this are ease of use, the need to install CUDA dependencies, which can be tricky, and the need to install Rust. So you can see here, after selecting our model, creating a Docker volume, and creating that token to be able to access LLaMA, we can run the image from the Hugging Face Hub. If you try to run that, you'll notice that you can't run Docker in Colab. So the alternative is to use the terminal, install Rust and the CUDA dependencies, and run it yourself. That's a little bit more complex and beyond the scope of this video, but I've included a guide that you can see. The other thing to note is you probably shouldn't have an LLM inference server running in a Jupyter notebook. So maybe it's for the better that we need to run this on a separate VM or in a containerized environment. Now once we have the server up and running, you can send a request to it. It's quite simple. As an HTTP request, you include the headers, the data you want to get, and just send it to the local endpoint. And afterwards, you'll get a response. So that's a quick explanation of TGI, an LLM inference server. In the next video, we'll talk about another one called VLLM. In this video, we're going to discuss another large language model server called VLLM. In 2023, this blog post came out, promising easier, faster, and cheaper LLM serving with a technique called paged attention. If you remember from a previous video, we talked about paged attention as a way of saving states for our large language models. If we scroll down, we can see the performance impact. Compared to TGI and native Hugging Face serving, VLLM has much better benchmarks. Due to paged attention and other key techniques, the authors were able to optimize serving in an easy-to-access manner. Now, VLLM is an open-source project. We can see it here on their GitHub page, at github/VLLM-project. Now, we're going to be implementing VLLM in our collab. It's actually the easiest server to implement from my experience. So let's head over to our notebook. I'm here in our notebook, which is from Chapter 4, 0404b. Let's start off by installing VLLM. I'm going to go ahead and connect to our T4 GPU in the top right. I'm going to install VLLM. Now this will take a little bit of time, since we actually have to update our CUDA dependencies. All right, here we go. We have successfully installed our packages. You might have noticed here that we had to replace some dependencies, so that's why it took longer. Now scrolling down, we're going to import VLLM. We're going to set up our prompts and our sampling parameters to know how the model will output the responses. Then we're going to run the LLM. So let's get started. I'm going to run this cell, and we've imported our dependencies. Let's set up our prompts and sampling parameters, and load our LLM in. Now you might remember from a previous video, we needed to add our secrets into the secret manager on the left here, which is our Hugging Face token. Otherwise, we might get an error when trying to import LlaMA. Alright, we have initialized and downloaded our LlaMA model, but we got an error. Let's scroll down and see what it is. So we got that the model's max sequence length is larger than the maximum number of tokens that we can store in the KV cache. So if you remember from a previous video, we talked about the KV cache as a way to maintain the model's performance and throughput. So let's go ahead and lower this by setting it to 128. I'm going to scroll up, set this to 128, then let's restart our runtime to free up our memory. Once it's restarted, I'm going to go ahead, reinstall our dependencies, import them, and rerun this command. Alright, here we go. By reducing our max model length, we have freed up enough memory to create our KV cache. Let's go to the next line. We're going to generate our outputs by running our prompts. Let's hit Shift-Enter. There we go. We have our responses. Now let's go ahead and generate our outputs for the next section. I'm going to hit Shift-Enter. And there we go. Looks like we got the responses for each of our prompts. Now let's scroll down to the next section, which is running the server. And what we can do is rather than running this as a simple Python command, we can actually start up a fast API server. Now to do this, we're going to restart our runtime, pass in our Hugging Face token as an environment variable, and set our max model length to 128. So let's go ahead and do that. I'm going to go to our secrets, copy this value, and paste it here. So let's go ahead and restart our runtime by going to the top, restart session, and then we can go ahead and run this cell. Alright, here we go. Our server is running. Now the challenge is that this is consuming the Jupyter Notebook's active thread. So to do a curl command to the server, we'll need to do this from the terminal. So let's scroll down and copy paste this curl command. Now on the left hand side, I can see I have access to the terminal. You might not have this feature, so you might need to upgrade to Colab Pro. But otherwise, you can just follow along. Let's go ahead and paste it into the terminal. We're going to send a request to our LlaMA 2 model with the prompt, San Francisco is a, and we'll see what we get. Let's hit enter. And here we go. We can see our response. San Francisco is a city that is known for its many attractions, and so forth. If we close the terminal, we can get some logs from the server. We have our average generation throughput as long as any requests that we got. That's pretty cool. So there we go. That's how we can install and run VLLM. It's quite simple to do. Now in practice, you'd probably run this in a containerized or virtual machine environment. But from this video, we've learned on how to install and run this awesome package. In the next video, we're going to go on to our third LLM server, which is Microsoft DeepSpeed MII. Let's cover a third LLM serving framework called DeepSpeed MII. You might be familiar with DeepSpeed as a way to train and run models, but recently Microsoft has made an update to make it even faster. I'm here on the GitHub page to take a look at some of the features of DeepSpeed. If we scroll down, we can see some charts about how fast DeepSpeed is. Compared to the previous serving framework we covered, it's up to 2 times faster, depending on the model. Some of the key features include KV caching, continuous batching, dynamic split views, tensor parallelism, and additional CUDA kernels. So we're going to use this framework to run LlaMA 7 billion parameters. Let's head over to our notebook. I'm here under 04_05, and we're going to be running MII in our collaboratory notebook. Now before we get started, let's walk through two pieces of information. Now on the left-hand side here, we have our Secrets tab. So for MII, we need to store our Hugging Face token as an environment variable. So similar to how we got it from the Hugging Face settings, we're going to paste it here under our secrets. Now the second item I want to call out is that MII is built for the more recent generation of NVIDIA GPUs, starting off with the Ampere architecture. So if you go to the top right here, you can see that I'm running an A100, which is a newer graphics card. To run an A100, I needed to upgrade my Colab notebook. Now the reason I can't run LLaMA in T4 on MII is because it's only supported in the MII legacy package. You can see in my notebook, I've linked the GitHub page here, and you can read more about it. But as we move to more modern architectures, this shouldn't become an issue. So let's go through and run this notebook. I'm going to click the top at runtime, and click Restart Session and Run All. So first I'm going to install the DeepSpeed dependencies. You may get a pop-up that says, please restart the runtime for some packages to take place. I've already done that. If we keep scrolling down, we can see here it took us 17 seconds to load our Meta LlaMA LlaMA 2 7 billion parameter Hugging Face model. Now I already had this model downloaded, so it took less time. Once we have our pipeline up and running, we can go ahead and run some inference. I ran two different pipelines here. DeepSpeed is and VoiceFlow is. Now looking at the result of these prompts, we can see here that LLaMA didn't do the best job. DeepSpeed talks about some high-performance computing, which isn't super relevant to our context. On the VoiceFlow side, the completions are quite different and strange. Let's go ahead and change it to some more standard questions. Let's add, why is the sky blue? And what is 2 plus 2? And hit Shift-Enter. All right, so first we can see here there's some article about physics education. Now that doesn't seem to be too relevant. And now the result for 2 plus 2 is equal to question mark. Okay, so not the best responses from LLaMA, but we still got to run this pipeline very quickly. If we scroll down to running MII as a server, this is a similar challenge to some of our other frameworks. Because this is a server, it's not meant to be run within a notebook. So you can see here, I have some errors as I'm starting it up. In the case that you do want to run it as a separate server without just a Python process, you can run it on your own VM or containerized environment. So within just a few lines of code, we learn how to serve our LLaMA model using the MII framework. In the next video, we'll dive deeper into some serving techniques that utilize LoRa and SLoRA. In our chapter about training LoRa models, it's pretty interesting to see that we could create multiple adapters. In this video, we're going to talk about how we can serve many LoRa models using the Hugging Face framework, as well as another technique called SLoRA. I'm here on the Hugging Face documentation, and we can see here we can add a LoRa adapter to a model. Scrolling down, we can also see that we can add another model. That's pretty interesting. And we can actually cycle between these two adapters to get different responses. Scrolling further, we can see that we can actively enable and disable these types of adapters. So in theory, we can serve many models at once using our base model and then adding adapters on top. That's pretty cool. Now let's head over to this framework called SLoRA. I'm on their GitHub page. Now the interesting idea behind SLoRA is that you can serve many more LoRa adapters at once. This is pretty powerful. In this diagram, we can see here that SLoRA achieves a much higher throughput for serving thousands of LoRa adapters. This comparison is done against the Facebook PFT framework, which you've seen before, VLLM, which we've also used, and SLoRA. Now you can imagine this use case if you're a model provider and you want to host many models. Imagine you're at a company and every team can fine-tune its own models. If everybody wants to host their own models, rather than running their own base instances of LLaMA, you can have a framework that takes in those adapters and serves them all concurrently. That's really cool. Now, the era of serving LoRa adapters is still pretty early, but progress through these different techniques will adapt us to serve large language models that are configurable in a much easier fashion. Now, serving LLaMA models can be quite complex. So rather than doing it all yourself, in the next video, we're going to cover how we can use a vendor to serve our LLaMA models. So far, we've worked with LLaMA both in a chat setting on Hugging Face and running it locally in a collab. In this video, we're going to discuss how we can use a vendor for accessing LLaMA. So let's go ahead into a GitHub project. I'm here on the Ray project on the LLM perf leaderboard. What this repo does is benchmark how quickly LLaMA models are served by different vendors. As you can see here, 8 different vendors are benchmarked, and all of them offer a solution to run LLaMA. More recently, the Grok set of chips and APIs have been shown to be fastest in industry, so I'm going to go ahead and try those out. I'm going to open up console.grok.com and log in. And I'm going to hit login with Google. Currently, Grok Cloud is free, but it has a pretty low rate limit, so probably shouldn't be used in production. So let's go ahead and create an API key by clicking on API keys on the left. I have one here already, but let's create another one. I'm going to hit create API key and call it using a vendor and copy this token. Now let's go into our collab repository. I'm in 04_07 under chapter 4. So I'm going to go ahead and add this key as a secret. I'm going to click add new secret and type in Grok API key and paste it here. And I'm going to exit. All right, now to run LLaMA from a vendor, whether it's Grok or any other, it's usually pretty simple. First, you need to install the Grok SDK, and afterwards, you can run the endpoint. So let's go ahead and do that. I'm going to hit run, and this will automatically connect me to a CPU instance of Colab, so this should be pretty fast. All right, we have installed Grok. Now let's go ahead and run the completion. Okay, something didn't work here. Now in this case, the way that Colab handles environment variables are they often need to be passed in. So let's go ahead and pass in the variable. I'm going to open up the secrets, grab this user data. I'm going to load the secret from the secret manager. I'm going to paste it up here. Copy this user data.get. And clean this up. Now let's hit enter again. So let's grant access to the secret. And there we go, we get an answer. Let's try to reprompt one more time. Let's say, why is the sky blue? And hit enter. All right, there we go, we get a response. Now we can truly see how quickly Grok works. Now whether you want to use Grok or another vendor, there are strong advantages to not running your own models. There are dedicated companies out there set up to run LLaMA for you. In the next chapter, we're going to dive deeper into the prompting of LLaMA. In this chapter, we're going to cover prompting with LLaMA. Now you might have used another large language model before, like Claude, ChatGPT, or Gemini. In this video, we're going to cover the differences between LLaMA and commercial LLMs. We're mainly going to focus on the prompting side, so let's get started. I have a number of different tabs open here. Let's start off with prompting LLaMA 2 in a chat interface. I'm on the Facebook Research GitHub page, under the LLaMA recipes. The first thing I want to point out is that LLaMA 2 Chat Edition has different instructions for system and user than ChatGPT. If we scroll over to our tick tokenizer, which talks about how ChatGPT incorporates the system and user prompt, we can see the formatting is different. Here's the ChatGPT one, and here's the LLaMA one. This means if you're writing chat-based prompts and not using a framework, you'll have to adopt this. Now let's talk about the second difference, which is model sensitivity to prompts. Now this paper is very interesting, since it talks about how much changing a prompt leads to the different outputs. If we scroll down to page 23, we can see some very interesting plots. We can see that LLaMA is much more sensitive than GPT 3.5, meaning that slight changes in the prompt, for example, different types of brackets, will immensely impact how good the responses are. This is pretty interesting. So whenever you're prompting with LLaMA, you need to spend more time doing prompt engineering and refining your prompts. Next, let's go through some prompting examples. I've asked ChatGPT 3.5, LLaMA 70 billion parameters, and GPT-4 to generate an answer on the question, what are better, cars or trains? Let's start off with ChatGPT 3.5. We get a paragraph-style response which answers the question. Generally, it's pretty good. Now with LLaMA 70 billion parameters, we get a longer response, structuring the information into advantages and disadvantages. Now GPT-4 gives us a long response that focuses on headers and identifying the pros and cons of each. Now reading through all these answers, they're all pretty reasonable. And this is one of the challenges of scoring large language models. How do you pick one that has the better answer? Now sometimes this is quite possible when you have a more objective prompt. Let's go to the next example. In this example, I'm going to ask LLaMA 2 to provide some classifications based on reviews. Let's hit enter. As you can see here, LLaMA 2 struggled with outputting the same format. We asked it to be in this review style format and not include any additional words. We still got an initial message and then got the review numbers without following this format. And for the same prompt, in ChatGPT, we got a better response. We didn't get an introduction, but we were missing that review tag at the beginning. Now in GPT-4, it followed it quite well. It gave us the reviews and classifications. Interestingly enough, only the ones without the classifications. And the fourth difference I wanted to bring up is pretty obvious. LLaMA 2 is an open source model. You can run LLaMA 2 on your own server, something that you can't do with ChatGPT, Gemini, or Claude. So overall, we've covered 4 differences between these models. The first one is how instructions are structured. The second one is the sensitivity of the prompts. The third one is how different prompts turn out in the different models. And the fourth one is how we can access these models. In the next set of videos, we're going to do more prompting work with LLaMA, starting off with few-shot learning. In this video, we're going to learn how to prompt LLaMA better. We're going to use a technique called few-shot learning. Few-shot learning is providing LLaMA with some examples. Let's dive in. Now I'm here in 0502 under our exercise files. Now I've already downloaded LLaMA just so we can get started. And let's scroll down to the exercise. So here, I've created a prompt to classify some reviews into different categories. My goal with this prompt is to have LLaMA fill in these colons to give me a response after each of these lines. So let's go ahead and run this notebook cell. All right, here we go. So our output starts here, and we really didn't get the results that we were looking for. Let's try again. Now because LLaMA is a smaller model, sometimes you'll get more chaotic responses. All right, here we go. We got something slightly better. We got classifications from our input, but it's not in the format we want. Let's check with LLaMA 70 billion parameters to see if it does better. I'm going to scroll up and copy this prompt. And I'm here in the Hugging Face chat using my 70 billion parameter model. Let's paste our prompt and hit enter. Now we can see here that the 70 billion parameter model outputted a much more structured response. Let's go back to our notebook. Now few-shot learning is going to help us structure our responses in a much better way, even with the 7 billion parameter LLaMA. Let's scroll down. So in this format, we're going to use these triple hashtags to denote an example. We have our review, and then we have our response. Now let's go ahead and try to run that. All right, here we go. We got a response. Now this response also isn't great. These triple hashtags are not well detected by LLaMA. Now if we go ahead and paste this into 70 billion parameters, it should work much better. Let's go ahead and create a new chat. and paste it in. Now this worked better, but we still got some additional information. This is one of those prompting differences between commercial models and LlaMA. An OpenAI model like ChatGPT would interpret these triple hashtags in a much better way, because that's the natural separator that those models use. A separator is a good way to denote the end of instructions and the continuation of some new ones. Now going back to our notebook, let's scroll down and change our prompt again. So at the top here, we've gone back to including our instructions, and I've added some additional ones to output with the same format in plain text, and also to not include any other formatting. In the bottom here, we have our reviews and our classifications. Now let's go ahead and try to run this. As you can see here, we got our response of random, and that's correct. Now something that you might have noted from this cell and the previous cell is I've included two different outputs. The first one is the decoded output, which includes both the input and output tokens. Then I also included a no input tokens output, which starts from when the prompt ends. So we can see here, this is our input and the output, and just the output down here. So this actually worked much better. We got exactly the response we wanted. Now the reason for this is because we demonstrated the format that we needed to LlaMA, and it provided the response. Now scrolling down, for another example, I'm going to use the LlaMA formatting of including instructions. In the previous video, we talked about the instruction tag. These instruction tags help to note when we start an example and when we end it. So in this case, this is the opening instruction tag and the closing one. And then the classification and promoter is the generated response. Now we included a couple examples, and we're going to run this. And here we go. We got another well-structured response. Now one thing to note is that I've included this S tag at the beginning. This denotes when LlaMA should start a response and end it. What LlaMA will do will generate the final S token to complete the sequence. And down here in my no input tokens decoded, and for our cleaned output, I'm also removing the -3 for this S token. Now scrolling down for a final example, in this one, I've included the system input that we've seen with previous large language models, having both the instructions and the system input. Now let's go ahead and run that again. And here we go. We got the correct output. So this is how we can use few-shot learning along with the different tags for prompting LlaMA to improve our output. In the next video, we're going to learn another technique called chain of thought learning. In this video, we're going to learn a prompting technique called chain of thought reasoning. By asking a large language model to think step by step, we usually get better results. Let's dive into our notebook. I'm in 0503, and let's start off with our prompt. Down here, I can see we have a prompt that says, if I have 2 chickens and 1 duck, how many bird legs are there on my farm? Now this is an interesting word puzzle. Let's go ahead and run this prompt. I'm going to hit Shift-Enter. Alright, here we get an answer. And this answer is pretty nonsensical. We have some random German in there, as well as some miscounting. Now if you run this prompt a number of times, you might get the correct answer, maybe 1 out of 10 times. But we want to get the correct answer in a consistent manner. If we scroll down to our next prompt, I've added think step by step towards the end. Let's go ahead and run this prompt. The goal of this prompt is to have LlaMA structure its thinking before outputting the final answer. So here we go. We have a little bit of nonsense at the beginning. We have our chain of thought reasoning with 2 chickens and 1 duck, and a total number of legs of 3. Okay, that's incorrect. Let's try one more time. And still incorrect, unfortunately. So we're making progress, but it's not where we want to be. Scrolling down to our next prompt, we're going to add an example. Similar to the previous video, I've added these instruction tags, wrapping an example that I want to give. We have our example between the instruction tags, and afterwards, we have an example of what thinking step by step looks like. So in this case, we're using donkeys and cows as an example. And finally at the end, we re-ask our question between our instruction tags. Let's go ahead and run this. Now in the previous times that I've run this, it works around 95% of the time, which is pretty good. Okay, let's check our thinking. So step 1, chickens have 2 legs, yes. Step 2, ducks have 2 legs, yes. Step 3, counting our chicken legs, we get 4. Step 4, counting our duck legs, we get 2. And step 5, adding them all together. 6 legs is the correct answer. You can see here the output is also much cleaner. Let's scroll down for one more example. In my previous example, I included a step for counting yourself. In this example, I'm going to ask LlaMA to include myself. Let's see what it gets. Alright, so LlaMA still didn't get this question right. This one's a little bit tougher and works around 70 to 80% of the time. But you can see that the thinking is still going. We're counting chickens, ducks, and yourself. Let's try one more time to see if LlaMA can get it to work. Alright, here we go. We got the correct answer. Now the formatting is a little bit funky, but with 2 chickens and 1 duck and ourselves, we have 8 legs. So in this video, we learned how to use chain of thought reasoning to better structure our prompts to solve more complex questions. In the next video, we're going to learn how to structure LLaMA's output to match with a Python schema. In this video, we're going to learn how to be more structured with LLaMA. Our goal is to be able to use schemas in order to structure our data. For this video, under 0504, our goal will be to get a Python object back from LLaMA. The steps are pretty straightforward. We're going to define a pedantic schema. We're then going to define a LangChain series of prompts. And finally, we're going to get a Python object in return. So let's go ahead and install our dependencies. We need LangChain, Grok, and LangChain. I'm going to hit enter on that. If you're not familiar with LangChain, it's a prompting framework which has lots of useful packages. So we're going to import our prompt templates and ChatGrok. We'll be using the API key we used in previous videos. You can find the key on the left-hand side, clicking on this key icon. So let's import all these dependencies. And we'll get to defining our pedantic schema. So we're using the pedantic output parser. First, we'll define a class, which is our base model. In our example, we're going to ask LLaMA to generate an animal and the things it likes to eat. So we've defined this class right here of animal and given it a field of name and another field of likes to eat, specifying the types for each. Next, we're going to define a query. Generate what foods a random animal likes to eat. Then we're going to feed this animal object into a pedantic parser. And finally, we'll generate our prompt by using the template, our input variables, and additional instructions. And here we're going to define our prompt chain with our prompt, model, and output parser. Finally, we're going to get our animal in return. So let's go ahead and run all these commands. All right, the moment of truth. What kind of animal do we get on this run? Still a grizzly bear. What does it like to eat? Salmon, berries, and honey. Now let's change our query a little bit so we get a different animal. Let's go ahead and scroll up to animal query and generate what foods a random animal likes to eat. Let's put period and say, make it a bird. Hit Shift Enter to run. Shift Enter again to run the chain. And get the animal. All right, it's a blue jay. And it likes to eat seeds, nuts, fruits, and insects. And there we have it. We were able to take our prompt, pass it through LLaMA, and generate a structured response that is now interpretable by Python. In the next video, we're going to continue leveling up our prompting skills by using a prompt automation framework called DSPy. Now we've learned to prompt with LLaMA, but is there a way to better optimize our prompts? In this video, we're going to cover how we can optimize our LLaMA prompts with a framework called DSPy. So let's get started under branch 0505. So to run this code, I used an A100 GPU. You can use a T4, but it would take a very long time. So let's walk through this notebook. Let's start off with defining what DSPy is. DSPy is a prompting framework meant to abstract LLM programs. We can take a look on their GitHub page. Let's click on that and scroll down. Now, DSPy came out of a research lab in Stanford, showing that you can get very good results on prompts by automating their generation. Let's click on the paper. This DSPy paper is about building self-improving pipelines, and one of the models that they use is LlaMA 2 13 billion parameter chat. So let's scroll down, and the conclusion of the paper is you can dramatically improve your prompting between 16 and 40%. So let's go ahead and head back into the DSPy library. Let's go back to our notebook and scroll down. So in step 1, we install DSPy-AI as our new requirement. And next up, we download LlaMA 2 13 billion parameters. This one should fit on a T4 as well. Let's keep scrolling down and get to our dataset. Now, similar to the paper, we're going to do evaluation based on math questions from the GSM 8K dataset. I've only chosen a subset of the data, 30 questions for training and 20 for development. Now let's scroll down. So let's ask LlaMA to answer one of these questions for us. As you can see here, we have some chain of thought reasoning, but our answer is incorrect. LlaMA said $734 when it should have been $817. So LlaMA struggles with these types of questions. Let's keep scrolling down. Now in this cell, I just have some code that lets us run our quantized model rather than having to launch a server that DSPy normally requires. Let's keep scrolling. Okay, we're here at the fun part. So we're going to initialize our Hugging Face model using our LLaMA model and tokenizer, and then configure DSPy to use this model. And next, we're going to define our Python class. This is going to be a question-answer signature. What we'll do is we'll have an initial prompt that we define at the top, a question, and an answer, with some descriptions to give us hints. Then we'll define a chain of thought module so that we use this signature to generate some sample prompts. Now let's keep scrolling. In the next cell, we're going to create a teleprompter and do a model compilation in order to create an optimized chain of thought prompt. You can see here, it ran for around 3 minutes, going through 6 different examples. So then we got our optimized prompt. Next up, we'll run the evaluation on this optimized prompt. So using the dev set, we run the evaluation using a custom GSM 8K metric, which has some flexibility in calculating the answer. After running this for 15 minutes, we see that we get 25% accuracy on this benchmark. Now we can inspect our prompt and our answer. As you can see here, we have our starting instructions at the top, followed by these 3 dashes to separate each example. We have our initial format, and then we have our questions. Now we didn't pick out the ideal parameters to do this optimization, so you'll notice some of the reasoning prompts are missing. But that's okay. We can spend a lot more time optimizing these prompts later on. Let's keep scrolling. And here we go. We have our answer, and then LlaMA for some reason auto-generated another response, likely because the separator isn't what it's expecting. If we keep scrolling, if we just used a regular chain of thought reasoning prompt, we'd only get 3 out of 20 questions right, or 15%. If we use just a zero-shot prompt, which only included the question, we'd only get 1 question right. So with this automation, we're able to improve our answers from 5% to 25%, all without having to write these prompts ourselves. That's pretty awesome. Now the magic of DSPy is you can chain many of these auto-generated prompts together. It's a fairly comprehensive framework, so I recommend you learn more about it. With auto prompt generation, you have a wide skill set to take on the most challenging problems. Now in the next video, you're going to be given a challenge problem to auto-generate some data in a Python format. Your challenge is to generate e-commerce product tags with LlaMA. So going through the requirements, you're going to need to generate a list of e-commerce products. And each product should have a name and some tags that will be used for our website. I've included some starter code for this challenge. Now let's start prompting, and good luck. Now let's go through the solution to our challenge. Let's scroll down to the section where we had a to-do item. So for this challenge, we needed to add around 5 lines of code. The first item was to add an e-commerce item class. You could have called it something a little bit different, but based on our requirements, we needed a name and product tags. Then we needed to find another pedantic model, one that would contain all the products. Now we have our query and parser that were the same as before. Let's go ahead and run this code. Shift-Enter to run our chain, and see our e-commerce items. We have t-shirt, jeans, and sneakers, and our product tags for the first one are cotton, black, and medium. And there we go. We are able to take our e-commerce use case and adapt our LLaMA prompting with our pedantic schema to get the results that we needed. Congratulations on completing the course. We've learned some key skills on prompting, training, and running LLaMA. The open source AI community is rapidly evolving, so you can follow me on LinkedIn, where I share new models and techniques as they come out. You can also watch my other courses, such as building apps with AI tools. Let's keep learning about Gen AI and adding this key skill to our developer toolbelt.